Okay, so we're going to continue with 13.1. Um, so we want to graph part A here. Let's start with A. So we have x of t being t, y of t also being t, and z of t being t squared. So notice here that first of all, x equals y, and you can write z is equal to x squared, or you could write z equals y squared. They both mean the same thing because x equals y. So what this means is, first off, let's take the line y equals x. So y equals x is, well, in the xy plane, it's a line, but overall, it's actually this plane that passes diagonally through the z axis. So whatever curve we have, so the curve must lie in the plane y equals x. Well, I think the curve should hopefully be apparent now, but let's just plot a couple of points here. So if t is 0, then we have 0, 0, 0. T is 1, then we have 1, 1, 1. Well, plus, if we've got t equals negative 1, we have negative 1, negative 1, 1. T equals 2, we have 2, 2, 4. T equals minus 2, we have minus 2, minus 2, 4, and so on. And so you can see essentially there's this parabolic shape that's happening inside this plane. Let me draw that parabolic shape with another color. So we have something like this going on. So it's this parabola with these points. So here's 0, 0, 0. Here, say for example, 1, 1, 1. Somewhere here would be negative 1, negative 1, 1. So on and so forth. So it's this parabola in the plane y equals x. Okay, so that's and which way are we going? Well, it's hopefully clear that we're moving this way. From 0, 0, we're going to 1, 1, 1 as t moves forward in time. So we're oriented. Let me erase these little arrows at the top. That's a bit confusing. So we have these arrows. We're going like that. Okay, that is the graph for part A. For part B, we had cosine of t is x, y was sine of t, and z was just t. So what is happening? Well, we know that if x is cosine and y is sine, if we just restricted our attention to those, then we would just have the circle of radius 1. So this is if we just looked at x and y. But as t is going along, and we would be oriented counterclockwise if this was just in the xy plane. So, okay. Now, since as t is moving along, this curve is essentially rising. So t is our, imagine this is our vertical growth, vertical movement, because z is the vertical direction. So instead of doing this, what happens is we start at the bottom. So here's our xy plane, and say, for example, at t equals 0, we would be right here. If this, let's just put this as the x just to make it similar to this other drawing. And then we would be rotating and we would be growing in height. So we have what's called we have a circular movement, but the circular movement is actually going upward. So this is what's called a helix. It's a fairly well-known graph. The orientation is still the same, but it's curling upward. So you can think of kind of a staircase that keeps going upward infinitely, and that's what we have. So that's the helix. Okay, I'm just going to do one more example here. which is the intersection of two surfaces. So in general, if you have two surfaces, their intersection will be a curve. So for example, let's take z equals x squared plus y squared, which is a paraboloid. And let's take the plane, say z is equal to y. So we want the intersection of this is a surface 1, we'll call it. This is surface 2. So visually, what do we have here? I'll just maybe try to draw it anyways. So here's our paraboloid. And we're slicing that, so that's S1. Let me do S2 in red here. S2 is, here's a plane, well, it would go through, if this was the y-axis and this was the z-axis, then we would have a plane diagonally traveling downward like so, that would slice through this paraboloid. And this would generate some type of curve of intersection, so it would, intersect in maybe something like this. You would have at the actual intersection itself would look something like this, a curve. Okay, so this part would be the intersection. And the question is, how do you parameterize that? Okay, how do you parameterize that? Well, z equals y. So we have two equations. This is the visualization. How do you actually do this? Algebraically, here is z equals y, and we also have z equals x squared plus y squared. So let's set y to be t. So let's just set y to be t so that z is equal to x squared plus t squared, but then z is equal to y, so z must also be equal to t. So we have t equaling x squared plus t squared, and so x squared would be t minus t squared, and well, I guess the way this is gonna work out is that part of the parameterization is going to be in one, part of it's going to be in the other. So x here is plus or minus the square root of t minus t squared. And there's going to be some bounds on this. Notice here that we need t minus t squared to be greater than or equal to 0. And if we factor out a t, this means t times 1 minus t must be greater than or equal to 0. And if you draw the real line here, numbers that are less than 0, so if this is the t-axis, if t is less than 0, then you get a negative times a positive, which is overall negative. If t is beyond 1 also, then you get a positive times a negative. Here you're positive. So it turns out here t must be bounded between 0 and 1. And so that's what you get. You actually get, this decomposes because, well, put in a different way, this curve is, since it cannot be written as a function of x uniquely, we have to write it as two functions. So you actually decompose. So we decompose the intersection of z equals y with z equals x squared plus y squared into two parts. So the first curve would be x equals the positive square root of t minus t squared, z equaling t, y equaling t. And the curve 2 would be x equals the negative square root of t minus t squared, z being t and y being t. And these curves together, C1 union C2, describe the overall intersection. So I wanted to do one example where we have an intersection of two surfaces, and this one gets a little more complicated than some of the ones I've assigned, but it's a good example. So let me leave you with one exercise for intersections of surfaces. So let's take the sphere x squared plus y squared plus z squared is equal to 1. And let's intersect with z is equal to y, the same other plane, and go ahead and try to find. So here actually you can do a full parameterization. So go ahead and parameterize as a single curve. We'll call it C of t. Instead of, so here in the previous example, I suppose it's possible to write this as a single curve, but what we're going to do is we're going to go ahead and say, okay, this one, it is a bit more challenging to do this as a single parameterization. It's probably possible, but a priori I don't see it. This one is a little bit more straightforward to parameterize, the sphere one here that I'm given. And so go ahead and try that. We will do that. This is pretty much, by the way, the end of 13.1. We'll do that example and then start 13.2 in the next video. So till then.